I am very glad to be able to introduce John Heilbron at this public lecture. Aside from being an occasion in its own right, of course, the lecture signifies several things. It is part, naturally, of the celebration of the 100th anniversary of the Bohr atom. More specifically, it launches the Niels Bohr Archive's International History of Science Conference, which celebrates the same occasion and which I am grateful that the Royal Danish Academy of Sciences and Letters has agreed can be held in these historical premises. John's lecture is also a celebration of the publication of a book marking the same 100th anniversary, Love, Literature, and the Quantum Atom. Niels Bohr's 1913 trilogy revisited, which I am proud to say is a result of a collaboration between John and myself. The book will be published on 18 July, but can be pre-ordered 20% off the normal price on forms that you can pick up on your way out, together with another book in Danish, Bohr på ny, celebrating the Bohr centennial, of which I am co-editor. That was the, yeah. Back in 1969, at a time when I, for one, had hardly heard about Niels Bohr, John wrote an extensive and important article together with his teacher, Thomas Kuhn, still famous for the book Structure of Scientific Revolutions from 1962, published. The article was published in the equally path-breaking journal Historical Studies in the Physical Sciences, of which John became editor many years later. For decades, John has been one of the most productive and respected scholars in the history of science, moving between centuries. In order not to take the whole afternoon, let me just say here that his latest book is an extensive biography of Galileo, shedding entirely new light on the Italian scientist. He has maintained an interest in Bohr, and when a few years ago I was given permission by the Bohr family to write an article for the centennial on the basis of the otherwise closed collection of early letters between Niels Bohr and his fiancée Margrethe Nørlund, this started a collaboration between John and me to collaborate on the book that has now become reality. The book consists of 3 parts. The first, by me, uses letters to depict the Niels-Margrethe relationship and its importance up to the publication of the atomic model. The second, written by John, uses the published letters and other material to put a new twist, an entirely new twist, I would say, on the understanding of the background of Bohr's atomic model in relation to his and Kuhn's old article and whatever has been written on the same matters since. It's not a few things. And the final part of the book is a reprint of Bohr's 1913 trilogy, which is really what we celebrate this year. Since the publication of the book, John has gone even further in his historical analysis of the background for Bohr's early work. We can look forward to what he has to say today. John will be speaking for about an hour, whereupon he has agreed to answer questions. Thank you very much, John, for agreeing to come here. And enough said by me. Let me now give the word to John Heilbron.
Thank you. Can you hear me? Yes. Thank you very much, Finn, for all those kind remarks and for the invitation and honor to open this colloquium, symposium, conference in honor of Niels Bohr. I'm also honored at the venue that I find myself speaking in, and I had intended to say that I was unused to speaking in sunlight because I live in England, But now I feel right at home, and you'll be able to see the slides more clearly. The quotation in my title comes from a letter from Niels Bohr to Margrethe Nørlund. It dates from February 1912, just before Niels caught the train from Cambridge to Manchester. He was on his way to arrange a transition. It turned out to be a quantum jump between the domain of Sir Joseph John Thomson, and whom Bohr ranked as a pioneering genius, and the domain, the laboratory of Sir Ernest Rutherford in Manchester. Both of them by then had won Nobel Prizes. It was a special moment for Bohr, for as he had not made a perfect success of Cambridge and hoped for a better outcome at Manchester. The prospect of a new start and a chance of showing himself to be the man of genius his family and his friends took him for would seem to explain sufficiently the rhetoric with which he described his frame of mind to Margrethe. My courage is ablaze so wildly, so wildly. In fact, his correspondence with Margrethe is full of blazing courage and boiling blood. He had arrived in England to work with Thomson with all my stupid wild courage. His blood boiled at the sight of King's College Chapel, Cambridge, a pillar in St. Giles Cathedral in Edinburgh, the Forth Bridge, not from irritation, but because great human achievements fired up his spirit of enthusiasm. When he glimpsed some progress in his physics, his blood could get feverish, or so he wrote to Margrethe, with apologies for his silliness in growing incandescent over so little. Many other stimulants could produce this ebullience. The great works of Goethe, Shakespeare, Ibsen, and Kierkegaard, grand scientific syntheses like the electron theory of Hendrik Lorentz or Joseph Larmore's Ether and Matter, an opera, a friend, a sense of well-being. After attending an opera with a colleague one fine November afternoon, Niels wrote semi-poetically to Margrethe, "My courage these days is ablaze, competing with the autumn sky and with all those things that by turn run through my silly head." From all of which you will deduce that young Bohr was a bold and a passionate fellow. The transition to Manchester started Bohr on the path to his quantum atom, brought him the success that had eluded him in Cambridge, and resulted in a revolution in physicists' approach to the micro world. In the first section of my talk, I'll try to specify revolutionary aspects of this approach as contained in or implied by Bohr's first paper on the constitution of atoms and molecules, which was published in July 1913, almost a year to the day after he switched his research field from the electron theory of metals to the theory of atomic structure. It's working? Yes. Here is the title page of his first paper in his trilogy. After identifying the revolutionary aspects of the paper of 1913, with the authoritative help of Einstein and Rutherford, I'll try to delineate the intellectual and psychological furnishings of the mind that could comfortably destroy the accepted treatment of a wide range of physical problems and replace it with a revolutionary scheme for which a very limited computational success was the main attraction. In this attempt, my attempt, and it's only a trial, I'll make use of some hitherto unavailable family correspondence of which you have just heard, and I believe it's possible to buy a copy of this book. Is that true, Finn? Yes. You have seen this, but I'll show it to you again. We all owe thanks to the Bohr family for allowing study of this unusual documentation of the sources and course of scientific creativity. A key factor in my account is a concept of partial truth, which can be traced backwards to roots deep in Danish culture, like Kierkegaard's Stages on Life's Way, and forwards to the four conflicting foundations that Bohr offered for the quantum postulate that underlay his computational success. I'll end by sketching how furnishings of Bohr's mind apparently far from physics, could have helped him to create his quantum atom, and what is not the same thing, to reassure him of its correctness. In sum, during the next 45 minutes, I shall be foolhardy enough to undertake to discuss these matters. I begin with the revolutionary aspects of Bohr's atom. To say what we all know, Bohr's quantum model of the hydrogen atom allows its single electron to occupy a series of discrete, special, stationary states, to give it the name he gave them, in any of which it can rotate around the atomic center without radiating or otherwise losing energy by collisions or any other way, but otherwise following the rules of ordinary physics. Radiation occurs when it jumps from one state to another of lower energy, and what is singular about this radiation occurs at one and only one frequency, or color, determined solely by the electron's loss of energy, or less insipidly expressed by the number of stationary states it jumps over. So the electron is either in a stationary state or it's nowhere. This way of picturing things seemed a fatal flaw to the first physicist to read about it. This was Ernest Rutherford, to whom Bohr sent a draft of his revolutionary paper. Here's what Rutherford wrote. Your ideas about the mode of origin of the spectrum of hydrogen are very ingenious. There appears to me one grave difficulty in your hypothesis, however, which I have no doubt you fully realize, namely, how does an electron decide what frequency it is going to vibrate at when it passes from one stationary state to the other? It would seem to me that the electron knows beforehand where it is going to stop so as to adjust its color of radiation. For Rutherford, whose strength as a theorist lay in picturable models and robust common sense, an electron that knew its future was as inconceivable as a frequency without a vibration. Here then is a clue to one revolutionary aspect of Bohr's quantum atom. It required physicists to renounce the project of understanding the radiation process if understanding requires a physical picture of events. Not even God knows what an electron is doing between stationary states. As Einstein remarked, the situation was even worse than the withdrawal of one facet of electronic behavior from the scrutiny of physicists. We know Einstein's initial reaction from a letter from the chemist George Hevesy, whom Bohr met in Manchester and who much later, of course, was an ornament of Bohr's institute here in Copenhagen. When Hevesy told Einstein that spectroscopists had confirmed Bohr's calculations, then, according to Hevesy, Einstein was extremely astonished. And he told me, then the frequency of the light does not depend at all on the frequency of the electron. This is an enormous achievement. Einstein had pinpointed the distressing disconnection of the frequency of the emitted light from the orbital frequency of the electron supposed to emit it. And indeed, since the irrational jump involves the frequencies of two different orbits, and the color of the light liberated by the electron is of one frequency, obviously its frequency could not equal both of the orbital frequencies. From now on, to avoid confusion, I will speak of the frequency of the light as color. That's what goes into your eye. And by frequency, I will refer to the motions, the hidden imaginary motions of the electrons in the atom, which are supposed to be associated some way with the light. The relationship between the frequencies of the participating orbits, the ones between which the jump occurs, and the color associated with the electron passing between them is in general quite distant and opaque. But that did not prevent Bohr, as you will see, from suggesting a way of reconciling color and frequency in one of the four conflicting foundations to his quantum atom, which I will discuss later. When describing the distancing of color from frequency as an enormous achievement, Einstein may have had in mind Bohr's freeing of radiation from its usual design in the physicist's world picture. According to this design, echoed in Rutherford's reaction to Bohr's quantum jump, A radiating electron directly stimulated a vibration whose color was that of the electron's frequency. The distancing of color from frequency consequently deprived physicists of the conceptual tools with which they were accustomed to handle the extensive domain of radiation phenomena. That was agreeable to Einstein, of course, whose light quanta did not involve vibrations in the medium through which the radiation traveled. To Bohr, also, the disconnection of the color of the radiation from the frequencies of the electrons in the participating stationary states was the most revealing and distinctive feature of his atom. In this revelation, he said, he was merely the messenger. It was the microworld that compelled physicists to shelve the tools of their trade. As Bohr put it, we have been forced to assume that a system of electrons will emit and absorb radiation of a frequency different from the frequency of vibration of the electrons calculated in the ordinary way. That did not bother him at all, for it expressed the irrationality that he expected to find when physicists pushed theories too far. I turn now to some of the furnishings in his mind which would have caused him to have this opinion. Einstein was not a timid physicist, but he acknowledged Bohr as his better in boldness. He told Hevesy that he had once contemplated ideas something like Bohr's, but drew back, not having the pluck, as Hevesy expressed it, to develop them. Where did Bohr's intellectual courage, not to say recklessness, and his confidence in his reasoning come from? The new material that Finn has excerpted, especially the letters to Margrethe, opens approaches to an answer. Bohr's reaction to her gift to him of Thomas Carlyle's bombastic book on heroes and hero worship is a good place to begin. Carlyle's heroes include the Norse god, man, Odin, and lesser mortals like Mohammed, Luther, Cromwell, and Shakespeare. Margrethe apparently saw some resemblance between these overachievers and her Niels. He liked the first chapter on Odin because, as he put it lukewarmly, everything about the Old North made his blood boil. But he soon grew tired of Carlyle's noise and nonsense and said so. Margrethe must have been affronted, since her hero felt obliged to apologize. Here is what he wrote. That is for the amusement of those who can read it. You ask what I meant by what I wrote about Carlyle. By comparing his style with a sermon, I just mean that one does not demand from a sermon that everything in it should be true. In the same way as from a great work of literature, there exist so many truths. With a sermon, the main purpose is to show your sympathies and make others enthusiastic about them. And that can, of course, be as important as trying to create something which one calls greater, that is, more universally human, and the truth of which will be of a somewhat different kind, coming closer to the so-called scientific truths, which again are of a somewhat different kind. This is so stupidly and badly put, but it is something I feel very strongly about. I can almost call it my religion, that I think that everything that is of any value is true. Although Niels did not state the source of this religion, it is easy to spot parallels to its sparse dogma in the teachings of the philosopher Harald Hoffding and Hoffding's friend and admirer William James. Connections of this kind have been proposed before by Jerry Holton, for one, and Ludwig Feuer, to provide a background for Bohr's later philosophy of complementarity. They have the support of a few textual parallels and several suggestive facts. Here are a few of the facts. One, Hoffding and Bohr's father often discussed high-flying philosophical questions when Niels was present. Two, Niels took a course or courses with Hoffding and always thought highly of him. And finally, Hoffding's formulation of philosophical problems helped guide conversations at meetings of the Ecliptica Club, a society of 12 overachieving students to which the Bohr brothers and several of their close friends belonged. These facts and the textual parallels have not summed to the hard evidence needed to convince hard-headed historians that Bohr's physics owed something to his interests in literature and in problems in philosophy emphasized by Hoffding. The letter from which I have just quoted, however, which hints at a man at home with multiple points of view, leads us directly to certain texts of Hoffding and James. An obvious candidate is Hoffding's Problems of Philosophy, a short and readable presentation of his wise approach to the great problems of life. Here is the wise man. It is hard to believe that Bohr did not know the content of this little book, which was published in 1902. In a long chapter on the nature of truth, Hoffding makes clear that no single system, no one set of truths can image or mirror reality. A single exhaustive account of reality lies beyond human capacity. Truth is a word for a successful analogy between things in being and things in thought. And as there are many possible analogies, there are many possible partial truths. Their value lies in the very practical business of making intelligible experience possible. Or, in a formulation that Bohr echoed in the fourth formulation of his postulate, our expression of truth must always be symbolic and therefore multiple. James says similar things more succinctly in his lectures on positivism, which date from 1906. The truth, he says, is the name of whatever proves itself to be good, that is, whatever has value. Exactly the words that Bohr used. This definition allows for, indeed requires, many truths. The whole notion of the truth, says James, is an abstraction from the fact of truths in the plural. That is a generous but not a sufficient account of the matter, for how do multiple truths or partial truths sum or cancel? The question, according to James, was wide open. We must overhaul the very idea of truth, he wrote, for at present we have no definite idea of what the word may mean. Bohr took up this congenial challenge, whether he found it in James or not. We know from a letter to Margrethe that by 1911 he was confident enough in his answer to this big question to expose it to the criticism of mathematicians at a lunch party at Cambridge. Imagine how pleasant the party was. None of the mathematicians, however, he reported, had ever heard the like before. Apparently, they had not read Hoffding or James. Here is a second example of the suggestive material in the excerpted texts. It concerns real religion, organized religion, which Niels repudiated when a teenager. Although his mother was a non-practicing Jew and his father, who bore the name Christian, was an atheist, they brought Niels up in the Danish state church in order, as he later said, that he not feel different from other boys. With his characteristic compulsion to get to the bottom of things, Niels took to religion more readily than either of his parents might have welcomed. He tried very hard, so he later wrote Margrethe, to believe in the Lutheran faith and the salvation of his soul, to understand what salvation might mean, and to divine why it depended on acceptance of arbitrary and improbable stories. But as James wrote, God's animal spirits are too high, his practical jokes too monstrous for rational reconstruction. The task overcame even Niels' powers to reconcile contradictions, and so, in an instant, suddenly, completely, discontinuously, Niels perceived that Christian dogma could not be true in any of the many senses of truth he could admit. When he confessed this leap into non-faith to his father, whom he idolized, he received a sage smile in reply. He recalled the episode for Margrethe. That smile, my little one, taught me a lot. My courage roared so wildly, for I knew then that I, too, could think. The approving smile of the man he most admired in the world taught him that he belonged among the few who could reason their way free from the standard beliefs of their class and culture, place and time. He would repeat the performance when recognizing that ordinary mechanics represented the truth of the micro world only a little better than conventional religious beliefs accorded with the meaning of life. Bohr's rejection of conventional religion brought as much distress to Margrethe's devout parents as his quantum atom would to classical physics. True to himself and to the memory of his father, who died in 1911, Bohr refused to be married in church. In a beautiful reply to an unhappy letter from his future mother-in-law, he touched on his theory of knowledge. There was a time when I completely believed every single word of what he was told in church, or perhaps more correctly, fought hard and victoriously with my doubts. Suddenly I understood that all of it was not true, understood it in a way that to me was beyond any doubt. But you must not think, oh, I forgot the entertainment. You must not think that I do not believe in anything at all. I believe that there is meaning in the world, a meaning that human beings cannot understand, but can only sense. And that does not make life poorer for me. On the contrary, it would be so infinitely trivial if I thought I could understand it. I further understand quite logically that there must be something a human being does not understand. The striking statement that a logical demonstration exists that proves the limitation of human understanding sends us back to the library. Here is Hoffding again. All understanding is conditioned by the relation between continuity and discontinuity, by which he meant between rational connection and arrangement on the one hand, and resistance to analysis, even impenetrability, on the other. The rational and continuous cannot completely render our experiences. There will always be something discontinuous, an irrational relation between the principles which may compose our consciousness and the being itself from which our experiences are drawn. Or, as James summarized Hoffding's position, facts are abstractions, completion is an ideal, neither is given in experience, nor can either be adequately supplied by our reason. So that above and below, from facts to wholes, thought fails to continue and terminates against an irrational. Hoffding's extensive demonstration of the irreducible irrationality at which all continuous thought must terminate rests on three arguments perfectly consonant with Bohr's views. One reaches the irrational by arguing that the contemporary program of reducing all phenomena to matter and motion must reach a point of discontinuity. Another arrives at the same place by examining the concept of causality. And a third, of which there are echoes in Bohr's writing long before complementarity, emphasizes the impossibility of a rigorous separation of the observing subject from the observed object. Not only is the distinction arbitrary, it is also regressive. For the subject is changed by the object into a new subject viewing a new object, and so without end. Here again, this is Hoffding, we run up against the irrational. And here perhaps we can see most clearly how inexhaustible being is in comparison with our knowledge. We will never comprehend it all. Kierkegaard says much the same thing, and even better, as Bohr could have read in Hoffding's succinct summary of the philosophy of the greatest of our thinkers. According to Kierkegaard, it is logically impossible for us to create a complete account of being because our knowledge and experience grow and change. And as we are part of the being we are trying to capture in thought, we are attempting to grasp something unformed or continually forming. Kierkegaard here snickered that academic philosophers had missed this point because they are such non-entities that they excluded themselves from existence in general. This is the problem of the subject altered by the object, a problem that, to continue the regress, can be followed into a story by Kierkegaard's patron, Paul Martin Müller. In it, as probably all of you know, a student addicted to thought drives himself into intellectual impotence by thinking about himself, thinking about himself, thinking. Bohr loved this story. In any event, so Hoffding's rendering of Kierkegaard continues, whatever understanding we achieve can only be retrospective. And not everything lends itself to backwards comprehension. We will never be able to explain how we can understand retrospectively the necessity of what was open-ended prospectively. This was to phrase the problem of the freedom of the will in precisely the same terms as Bohr later solved it by the doctrine of multiple partial truths. We are free in prospect, bound in retrospect. Kierkegaard regarded his main task as criticism, as raising difficulties about accepted beliefs. Among his preferred targets was the assumption that we can, I quote, make a smooth and continuous connection among the parts of our knowledge. That was wrong both intellectually and morally. It is only reprehensible laziness, says Kierkegaard, or impatience to believe that there must be something complete and closed that leads us to it. Bohr's letter to Margrethe's mother is in close harmony with Kierkegaard's criticism. He would also, this is Bohr, have resonated with Kierkegaard's claim that claim to the role of universal critic. For if there was anything at which Bohr excelled as a young man, it was criticism. The centerpiece of Hoffding's précis of Kierkegaard is the notion of distinctive and even discontinuous stages or types of civilized life. Bohr's blood boiled at a high temperature over one of Kierkegaard's presentations of this theme, a lively book entitled Stages on Life's Way. Here we are on unusually solid ground, because in 1909, Niels sent his copy of this book to Harald as a birthday present with a commendation that reads as follows: "It is the only thing I have to send. Nevertheless, I don't think I could easily find anything better. I think absolutely that it is about the most beautiful thing that I have ever read." Harald returned the book, Harald didn't share this opinion, in which one of Niels's grandsons, Thomas Bohr, recently found some manuscript notes. Although they are not in Niels's hand, they may yet be the critical remarks that, notwithstanding his admiration of stages, he told Harald that he had written about it. In another letter, he refers self-deprecatingly to scrap, which I take to be a further reference to his ability and proclivity to criticize. For a scrap, if that's the way you pronounce it, was the Old Norse sword so sharp it could cut through the toughest knot and the hardest steel without blunting its edge. Here is part of what Scrap wrote or may have written about Kierkegaard. "From my point of view, I must condemn his life and behavior while respecting his struggle and his work, whose fruit is among the most beautiful writing in the world." It's one of the reasons I think it comes from Bohr, echo of what he had written to Harald. "I, who do not feel in any way united with, even less bound to a God, therefore am much poorer than Kierkegaard, would say that the good is the overall lofty goal. But, oh God, Kierkegaard, how rich a person you are." I'll return directly to what might have been meant by Kierkegaard's riches. First, however, I must say a word about Bohr's circumstances when, at the age of 24, he expressed himself so ecstatically about stages on life's way. He sent the book to Harald from a parsonage to which he had withdrawn from the hustle and bustle of Copenhagen to prepare for his master's thesis and examination. It was just the place for a romantic intellectual. "I walk here in solitude," he wrote Harald, "and think about so many things." He thought about physics, of course, and mathematics and logic, but also about the problem of cognition, the stages of life, the nature of the good. I assume that the document Thomas Bohr found is either a copy of the original written at the parsonage or notes taken there to Bohr's dictation, a method of working characteristic of him. The reference in the notes to Kierkegaard's riches returns us to the problem of truth. His insight into the human condition was so deep that he had to divide himself into a dozen different personae to do justice to it. These personae appear in his books as characters and on his title pages as pseudonyms. He needed 6 of them to convey the truths in stages. The earliest stage, the aesthetic, which for some unfortunate souls lasts a lifetime, is a period of carefree experimentation, of flitting from one experience or idea to another. Kierkegaard depicts it through speeches given by 4 of his atavars at a symposium on love, life, and the universe. Each says something true, though his statement conflicts with what the others say. Another avatar, a self-satisfied judge, sets forth the merits of a good marriage, the essence of the second, or ethical stage. The judge's wife was patient, understanding, supportive, protective, enabling him to reach the highest level his talents and training permitted. Neither he nor she could achieve as much apart as they did by pooling their complementary qualities. Each contributed an equal share to the truths of married life. Bohr needed such a partner more than most men. As for the third and final stage, the religious, it can only be reached by a leap of faith, which, as we know, was a quantum jump that Bohr took in the opposite direction. Another of Kierkegaard's personae made a perfect model for a romantic young critic walking in solitude around a country parsonage. This was Johannes Climacus, who had a passion for thinking so intense he could not think about girls. Instead, he worried about the meaning of the key of philosophy, the slogan, De omnibus dubitandum est. Having a romantic soul, which always looked for difficulties, that is, being a consummate critic, Climacus managed to prove that the foundational principle, modern philosophy begins with doubt, has no meaning at all. And if it did mean anything, it would exterminate the race of philosophers, since every student would be obliged to doubt the words of his teacher, and each generation would slay its predecessor. And so poor Climacus never advanced even to the threshold of received philosophy. He became more and more retiring, fearing that thinkers of distinction might smile at him when they heard that he, too, wanted to think. I would guess that the multiplicity of points of view and stages, all of which have some value and hence some truth, and Kierkegaard's invincible amor intellectualis, as represented by Johannes Climacus, were among the great attractions of Kierkegaard's aesthetic writings for Bohr. Bohr's mental furniture certainly contains some principal items from the workshop of Kierkegaard and Hoffding, and perhaps also of William James. This does not mean that Bohr was a thorough student of philosophy. Like Climacus, he never crossed the threshold of the profession. Nonetheless, he had a strong interest in a few philosophical problems as posed and answered by Hoffding, who in turn had a high regard for Bohr's philosophical acumen. Could it be that the young friend from whom Hoffding expected much in philosophical respects, and who around 1902 offered a criticism of his, Hoffding's, philosophy of religion, was Niels Bohr? Though only 17 in 1902, Niels had already assisted in the conversations between his father, Hoffding, and some of their colleagues, and not much later, Niels corrected a passage in Hoffding's textbook on logic. I fear that I may have created a monster in harping on the philosophical ideas that Bohr picked up during his adolescence and while studying at the University of Copenhagen. The letters to Margrethe document a lighter side, though perhaps overly intellectual for some tastes. They quote poetry to one another, Goethe, Ibsen, Shakespeare, and sometimes descend to Dickens' novels. Bohr loved adventure stories, and as a boy was addicted to the tales of James Fenimore Cooper. The ridiculous feats of Cooper's Indians and marksmen in the great American forest perhaps reminded him of the exaggerations of the Icelandic sagas, for which he also had a taste. And of course, there was Margrethe. Departing here from Johannes Climacus, Niels came to think almost obsessively about her as quidam in stages, the seducer in either or Kierkegaard himself in real life, did about their girlfriends. Niels and Margrethe became engaged a year or so after they met. But, as Margrethe understood perfectly, hers would be a ménage à trois. She would have to share Niels with his work. In reply to a question put to her several times in their letters, she acquiesced in this arrangement and professed in so many words to love his work as she loved him. She began early, even before marriage, as his amanuensis. She bore the test cheerfully when spending her honeymoon in Manchester, helping Niels to finish a paper on the life history of alpha particles. Before her marriage, Margrethe had worried that she might not know enough or be able to learn enough to be a companion to a compulsive thinker in his thoughts. Her future mother-in-law assured her that she did not need to know anything except the value of intellectual work. Here is what Ellen Bohr wrote her future daughter-in-law. "You are so genuinely good and also wise precisely because your soul is so sensitive to everything really good and wise. Wisdom is not the amount of knowledge, but the understanding of and love for the value of intellectual work, which is so rarely valued because so few know what it requires of strength, diligence, and unselfish striving." You know what a rare treasure Niels is. I come now to try to connect these remarks with the revolutionary aspects with which I began. In the interest of time and clarity, I'll conclude with a caricature of the way Bohr's special mindset could have assimilated and transformed the conflicting ingredients that formed his quantum atom. A caricature, of course, is not an untruth, but an exaggeration designed to bring out some features of truth at the expense of others. A good caricature is a memorable expression of a partial truth. And although I certainly do not claim that mine is memorable, I can say that it is fitting. For what, after all, was Bohr's quantum atom but a caricature contrived to bring out certain aspects of the micro world? The caricature, that's Bohr's, begins with the nuclear atom and its rings of electrons. The structure as Rutherford left it lacks an essential ingredient. There was no way to calculate its size by the quantities characterizing its parts, that is, the charges and masses of the electrons and the nuclei. Ordinary mechanics allows the electrons to revolve about their nucleus at any distance they please. Yet all atoms of the same element, when in their ground or permanent states, are identical. But then again, ordinary mechanics does not allow permanent states for electrons revolving about a nucleus, or stationary states. It requires, rather, that an electron constrained to a circular orbit revolving about constrained to a circular orbit must radiate, lose energy, and fall into the nucleus. So, classical nuclear atom may be temporarily as big as the solar system, but eventually as small as the nucleus. And to overfill the cup, a nuclear atom containing more than one electron is radically unstable against small disturbances that cause the electrons to move away from their orbits. So if they oscillate around their orbits as they go around the nucleus, eventually those oscillations will grow so big, the atom will fall apart. These several disabilities only made the nuclear atom more attractive for Bohr. They brought out very sharply the partial truth that ordinary mechanics did not work in the atom and located the general places of its failure. The year before Bohr, delighting in its weakness, took up the nuclear atom, a panel of distinguished physicists met in Brussels under the auspices of Ernst Solvay, a tycoon of the chemical industry and an amateur designer of world systems, to discuss the problems of radiation and quantum theory. The panel, which included Planck, Einstein, and Rutherford, agreed more or less that the constant that Planck had introduced into radiation theory to obtain exact agreement with measurement was connected with the size of atoms. Bohr may have known of this conclusion from Rutherford, but in any case, in the first draft of his quantum atom, drawn up for discussion with Rutherford in June or July of 1912, Bohr fixed the size of atoms by requiring that in their ground state, every electron in them have a kinetic energy proportional to its orbital frequency. Put up some general equations and concepts, which you can follow or not as you please. So the first is the ground state condition that I just mentioned. In that state, by definition, the electrons had lost all the energy that nature allowed them to dispose of and therefore did not radiate. It's just a definition. Otherwise, they went around the nucleus as if they were planets circling the sun. Bohr told Rutherford that K, the constant, was some fraction of Planck's H, and he chose the condition in analogy to the restriction Planck had put on his radiators. Now, you all know, I'm sure, that a Planck radiator or oscillator is a greater caricature even than the nuclear atom. It is essentially an electron tied to a perfect spring. Planck's precept stated that the radiator or oscillator released or absorbed light of color nu only in units or quanta h nu, a limitation in conflict with the liberal policy of ordinary mechanics, which allowed an oscillator to have any energy, however small. Now, a perfect oscillator, this is important. A perfect oscillator of Planck's type has the same frequency, omega, that's mechanical frequency, regardless of its energy. So if you think of the resonator as a spring, no matter what its amplitude, if it's perfect, it has the same energy. And so this oscillator could vibrate at that same frequency both before and after it lost or acquired the quantum of energy h nu. That made it possible to equate omega and nu, that is, the color of the light and the motions of the electron, or the frequency of the motions of the electron, notwithstanding the quantum condition. At first, Bohr had no reason to distinguish nu from omega, for in his model of the ground state, the atom did not radiate, so no news. So he took the frequency of the electron in its ground state and its kinetic energy, which in a nuclear atom is the negative of the total energy, as the quantities required in Planck's precept, and so wrote T equals K omega. By limiting himself to the ground state, he minimized or disguised the ambiguity between color and frequency, and had a model with which to pursue the program established by his former teacher, J.J. Thomson, for a decade. This program was to account for the periodic properties of the elements by an atomic model. And even in his revolutionary paper, the one of July 1913, he specified that his subject was not the spectrum of hydrogen, but the behavior of atoms in their ground state. Bohr began to take radiation into account toward the end of 1912, several months after his return to Copenhagen. He did so in shocked reaction to the papers of a Cambridge mathematician named John William Nicholson. Nicholson had fixed the size of a nuclear atom containing a few electrons in a single ring by calculating the frequencies which they oscillated perpendicularly to the plane of their motion. Remember, the oscillations, small oscillations in the plane are unstable, will tear the atom apart. Ones perpendicular to the plane can be stable for certain numbers of electrons in the ring. Nicholson managed to match these frequencies of the electrons perpendicular to their plane of motion with a dozen or more lines in spectra from the sun's corona and from certain nebulae, that is, from sources not available on the Earth. From the match, he could calculate the orbital frequency of the oscillating electrons, and then, by ordinary mechanics, the atomic radius. He knew about the proceedings in the Solvay Congress, and therefore, he decided to try whether the size of the atom that he had deduced backwards from the match with the spectroscopic observations did indeed contain, in some form, Planck's H. And lo, it was so. In every case, the electron had an angular momentum equal to a small integral multiple of h divided by 2 pi. Nicholson's astonishing performance extended the purview of the nuclear atom well beyond the applications Bohr had in mind. Unwilling, however, to be deflected from his version of Thomson's program, that is, from his attempt to explain the periodic properties of the elements, Bohr worked out a compromise whereby Nicholson's atom described the radiation process and Bohr's the ground state non-radiating behavior. There just had to be some truth in Nicholson's model. It agreed well with experiment and married quantum theory to ordinary physics. It had value and therefore truth. Even after Bohr invented his own account of radiation and had discarded Nicholson's, he did not reject Nicholson's mechanism altogether and reinstated it to scatter light. Most importantly, absorption of Nicholson's papers raised Bohr's sights to higher stationary states he had not considered previously, in each of which an electron had an orbital frequency proportional to its kinetic energy. The second or third of my relations there. Also, Nicholson's condition on the angular momentum, if it were taken as an exact principle rather than an approximate empirical finding, allowed Bohr to infer that his new constant k sub n, which characterized each of the stationary states, was equal to nh over 2. It is said that chance favors a prepared mind. When, at the insistence of a younger colleague, Hans Marius Hansen, Bohr examined the Balmer formula for a series of colors in the spectrum of hydrogen, he saw how to bring exact measurement to the support and extension of his quantum atom in perfect harmony with his expectations about the limits of physical theory. The Balmer formula reads in its most suggestive form, as you see it in the bottom equation. If you multiply both sides by h and read it as a Planck precept regarding quanta and energy, it immediately suggests that RH over n squared is the kinetic energy of a hydrogen atom in its nth stationary state. So it appeared that the radiation process was the locus of the quantum difficulty. Radiation did not take place by oscillation around stable orbits or by oscillation of electrons on perfect springs, but by abrupt transitions or jumps between them. And since the frequencies of the participating orbits differed, the color of the light emitted could not be equal to both of them, and in fact, it's not equal to either. Bohr then had a crisp dichotomy between stationary states in which electrons behaved as if Newton had designed the atom, and quantum jumps in which not even a Newton could follow them. With what satisfaction would a student of Hoffding's have contemplated this outcome? The master had taught that the world consisted of the continuous, describable, and rationally explicable, and the discontinuous, irrational, and novel. Here, in a simple case, Bohr had found one of those closed doors at which continuity must stop, or to adopt the words Niels used to reconcile his future mother-in-law to her daughter's marriage outside the church, a place where we confront the demonstrable truth that there are things human beings cannot understand. What struck Rutherford and Einstein as spectacularly bold conclusions were for Bohr only what was to be expected. That physicists had to renounce their ambition to give rational accounts of the physical phenomena, all physical phenomena, was in the nature of things as viewed from Copenhagen. The identification of the Balmer terms as energies of stationary states was one of two components that made possible Bohr's great computational success: the theoretical calculation of the constant R in the Balmer formula in terms of the charge and mass of the electron and Planck's H. Anybody who wants to follow it can do it. I call attention, however, to this one thing about the demonstration, and that is once you have the physical concepts, the rest is elementary algebra. Now, Bohr was too responsible a physicist to want to rest his derivation on so obscure a postulate as that the kinetic energy of each electron in a stationary state should be n/2 times h times the orbital frequency. So he offered a more basic foundation, or foundations. As already advertised, the grounding of the ambiguous truth of the postulate, T sub n equals nh omega over 2, required no fewer than 4 partial truths. 2 of these truths are analogies to Planck's radiation theory, one based on each of the chief formulations it had in 1913. The third partial truth brings the radiated color into asymptotic agreement with the frequencies of the participating orbits by requiring that at great distances where the electron is almost free of the nucleus, the color of the line given off when the electron jumps between nearest orbits is equal to the frequency as calculated mechanically from the mechanical or orbital frequencies. The fourth partial truth, or grounding, appears to be a mathematical reworking of the basic postulate into the familiar condition on the angular momentum of an electron in a stationary state. This is, of course, the only one of the 4 partial truths now remembered, if you wish to review. The grounding via analogy to Planck's precept contains whatever partial truth there was in Planck's radiation theory. As we know, the analogy does not fit the nuclear atom very well because of the difference between nu and omega, and Bohr soon gave it up as misleading. He came to prefer the asymptotic grounding, which he later generalized into the correspondence principle, which required that at some limit, classical and quantum calculations should agree. It contains the partial truth, or vague requirement, that where the domains of validity of contradictory theories overlap, the quantitative descriptions they give should coincide. The correspondence principle may appear to plug the breach between the micro and the macro world. It does not. For although the calculations agree, the physical pictures underlying them do not. The fourth grounding is not a mere reworking of the postulate in Nicholson's manner, and is conceptually quite different from the other 3 foundations. They mix together quantities pertaining to the radiation emitted and the motions of the electrons, somehow responsible for it, whereas the condition on the angular momentum relates only to the orbit. But it too is only a partial truth, as indeed are the electron orbits themselves. As Bohr put it in the paper of 1913, in a typically oracular phrase, while there obviously can be no question of a mechanical foundation of the calculations given in this paper, it is, however, possible to give a very simple representation of the calculation by the help of symbols taken from the ordinary mechanics. So, the foundation that is not a foundation is the condition on the angular momentum. The notion that symbols render partial truths harks back to Hoffding. As we all know, Bohr's quantum atom initiated a development that within a decade, taking time out for World War I, produced quantum mechanics and revealed to Bohr the philosophy of complementarity. This philosophy rested on the perception that partial truths come in pairs, not trios or quartets. Each pair has the property characteristic of Bohr's thought of being formally inconsistent and even contradictory, and yet necessary for a complete representation of experience. Thus, wave and particle, space-time and causality, as applied to the micro-world, and free will and determinism, and vitalism and mechanism, as applied to wider human concerns. These last extrapolations, which date from the 1930s, were not evidences of a turn to philosophy by a decaying physicist, but of a return to the broad questions that Bohr had encountered through Hoffding in the old days when he discovered that he too could think. Thank you very much for your time.